We live in a material world. And I don't mean just a materialistic world, although that certainly is true too, but a world made of materials, solids, liquids, and gases. The great principle of Lecture 25 is that the properties of materials depend on the type of atoms and the way they're bound together by chemical bonds. In this lecture, after a brief review of what I mean by properties of materials, I'm going to consider 5 critical kinds of properties that occur in the materials of our everyday world. These 5 properties are strength, thermal expansion, stickiness, magnetic behavior, and electrical conductivity. Now, the underlying theme of all of these different properties in my discussion is going to be that the properties of materials depend on their atoms and the way they're bound together. Let's begin by setting the stage. Where have we come from in the past several lectures? We began by considering the chemical elements themselves, and their properties, their behavior leads to the periodic table of the elements. And then the fact that some numbers of electrons designated by the filled shells of the periodic table are more stable leads to chemical bonding. We saw ionic bonding, metallic bonding, and covalent bonding, in which electrons are transferred or shared or given away in order to get more stable electron arrangements. We then saw that variations of temperature and pressure lead to the different states of matter, the solids, the liquids, of gases, that you could transform from one state to another. And finally, complete rearrangements of atoms in phase transitions and in chemical reactions. And these are fascinating because, like magic, they transform one material into a material with completely different properties. Think about this magic of phase transformations and chemical reactions. You can take a silvery metal like sodium, combine it with a corrosive greenish gas like chlorine, and form table salt. A white powder mixed with water becomes a loaf of bread. You can take a lump of coal and it will burn completely away to nothing but air, completely disappearing. And you can mix 2 different liquids together and form a polymer, a polyurethane foam that comes bubbling out of a container. Alchemists of the Middle Ages repeatedly tried, and they failed, to turn metals like lead into gold. But modern chemists have learned to turn these and other elements into a remarkable variety of materials that have transformed society itself. You see, materials are useful because of their distinctive properties. There's so many properties. There's color, hardness, flexibility, density, transparency, its texture, the electrical conductivity, the thermal expansion, the melting and boiling points, heat capacity, on and on and on. Indeed, any adjective that you can use to describe a material likely relates in one way or another to its physical properties. You know, materials are so important that we've defined key historic eras of human history by the major material that was in use. We have the Stone Age, the most ancient age when stone tools and weapons were in prominent use. And then came the Bronze Age. Bronze is an alloy of copper and tin, and that alloy probably was discovered quite by accident. Someone had a piece of copper and tin ore. If it fell into a fire, bronze may have formed spontaneously. But when it did, its citizens found this new, tough, resistant metal with which to make tools and weapons. The Bronze Age, by the way, was at different times in different parts of the world. In the Middle East, where bronze was discovered earlier, the Bronze Age lasts from about 3500 to 1500 BC, while in Europe it was more like 2000 to 900 BC. And then came the Iron Age. Iron takes much higher temperatures and a more sophisticated technology to smelt, but iron is a tough, strong metal to make weapons and tools. The Iron Age began at about 1500 BC in the Middle East. It began about 900 BC in Europe. These are ages named after materials. Now think about our own modern age, the modern age in human history, which is characterized by an astonishing variety of new materials. Just look around you at the materials of your world. The furnishings in your home feature many different kinds of inorganic materials, that is, metals, different kinds of alloys, all kinds of specialty glasses, all kinds of ceramics and pottery. You probably own hundreds of different kinds of high-tech organic materials, compounds like paints and glues, tapes, all the fibers that make up your clothing, fuels, dyes, insulation, medicine, cosmetics, soaps. Think about detergents you use to wash your clothes, inks, an amazing variety of plastics, so many kinds of plastics, and of course all the different kinds of fuels that we use to power our cars and so forth. There's so many different kinds of organic materials, thousands of them in your day-to-day life, just around you. And then, hidden deep inside your automobile, in your stereo, in your computer, there are semiconductors and other materials of the electronic age, materials you very rarely see but play a vital role in all our lives. Well, the distinctive properties of these and other materials are the result of the kinds of atoms and their arrangements in 3 dimensions, the structure, the way they're bonded together. For the rest of this lecture, I want to examine the close links between atomic structure and properties. And as I said, I'm going to look at 5 different kinds of properties. We're going to begin with one of the most obvious properties of any material, that is the strength of that material. Material scientists distinguish 3 very different kinds of strength. We have compressive strength, which is pushing on something, tensile strength, pulling it apart, and shear strength, which involves twisting. Now, as I said, compressive strength refers to a material's resistance to being crushed. Materials with very high compressive strength have to have a rigid framework of atoms. They have to be strong in 3 dimensions. And a great example is a brick, a piece of ceramic or a piece of brick or cinder block, something like that, a rock, which is extremely strong. It can hold up the weight of thousands of tons if you have a good, strong brick or stone foundation. Very soft or weak materials, on the other hand, have planes of weak bonding between the atoms. So many soft materials, which you wouldn't use to build your buildings, have those weak planes of bonds. A second kind of strength is tensile strength. That's what happens when you pull something apart. Materials with high tensile strength have to have a continuous chain of strongly bonded atoms or molecules. So polymers are particularly effective. And so you have, for example, rope, which is extremely strong, can hold hundreds of pounds when pulled because of these chains of carbon atoms that run all the way through. Now, you've heard the expression that a chain is only as strong as its weakest link, and the same thing's true with a polymer or any other kind of material with strong tensile strength. If you expose a nylon rope to sunlight, it gradually depolymerizes the rope. It breaks the strands in various places. And a nylon rope that looks perfectly strong can be tragically flawed. Indeed, I had a friend in graduate school who was killed in a climbing accident because he had left his nylon rope outside in the sun. Shear strength refers to a material's resistance to being twisted. Materials with high shear strength have to have an incredibly strong cross-bracing in order to prevent that kind of twisting, something like a trestle bridge. One of the most obvious examples of material with very high shear strength is diamond. We've seen this structure before. You can twist this structure because the 3-dimensional cross-bracing of atoms is so incredibly strong. That's the diamond structure. These 3 types of material strength don't always go hand in hand. And I think this may become obvious when I show you a few examples. For example, you can have a stack of bricks, which is incredibly strong under compression, but it has virtually no tensile strength unless it's mortared together. So you can push on it and it's strong, pull on it and it's very weak. This, in fact, is a problem with ceramic buildings, buildings made of cinder blocks or bricks, as we'll see in an earthquake. A nylon rope has exceptional tensile strength. You can apply hundreds of pounds to it, but it has no compressive strength whatsoever. You can't push on a nylon rope to support anything. Another example would be in the shear strength. A Coke can, for example, is very strong under compression when it's full. It's very strong under shear when it's full. If you twist that can, it won't twist. But as soon as you empty it of liquid, it becomes very, very weak. In many applications, a combination of these three different kinds of strength are required. Now, these considerations come particularly into play in design of earthquake-proof buildings. An earthquake is a sudden movement of the ground that sends a shock wave through the earth. Literally, the earth goes through waves, up and down, side to side. It subjects buildings to terrible stresses. It subjects them to shear stresses and compressive stresses and tensile stresses, all at the same time. Now, masonry buildings are very subject to damage and earthquakes because while they're strong under compression, under the weight of gravity, when they're twisted side to side, they easily break apart. This is why composite materials are now being used extensively in earthquake-prone areas. We talked about reinforced concrete with steel rods going up through concrete. That adds shear strength. Also, it's very simple in a wood building just to apply plywood. If you nail plywood sheets in between the framing, the plywood, which has layers of wood going in opposite grains, is extremely strong under shear and therefore resists earthquake damage much, much better than a normal frame building would. One thing you may have noticed is how minor defects in a material can greatly reduce its strength. A classic example is glass. You have the slightest scratch or nick on a surface of glass, and that can start a crack that will destroy a whole piece of glass. For example, your car windshield. And you may have seen that. You get a tiny scratch, a tiny crack, and it will propagate, weakening the entire glass structure. Our second physical property is thermal expansion. This is the tendency of materials to change their dimensions when they're heated. Now, thermal expansion is another property that's absolutely dependent on the behavior of the atoms and how they're bonded together. Most materials will expand slightly when they're heated. In these materials, like a bar of metal, for example, you have atoms side by side. And as you heat up the material, each of those atoms starts vibrating more and more and more vigorously and starts colliding and bumping into its neighbors. And naturally, this applies a force, and that force tends to make the whole material expand slightly. So the metal becomes larger and larger as you heat to higher and higher temperatures. That's the normal behavior, and almost all materials do that. But there are some very intriguing materials that behave differently. And these include materials that actually contract when they're heated. Now, how in the world could that happen? Think about this idea of contraction. You heat up a material, the atoms vibrate more vigorously, and yet the material gets smaller. It turns out these are materials that have very, very strong bonds between one atom and other atoms. And therefore, these bonds act like rigid sticks. At low temperature, there's very little vibration. And so the atoms are at their maximum separation. But as soon as you go to higher temperature, you get more and more vibration. The angles between the bonds get smaller. And therefore, the angle between the end members gets less as the material gets hotter. And this is what causes thermal contraction, a very interesting phenomenon of strong materials. The theme of this lecture is that the properties of materials are the result of their atoms and their bonds. And the close ties between atomic scale structure and physical properties are especially evident in the property of stickiness. And this is the third property I want to consider in this lecture. Now, we want certain materials to be sticky. We want inks and glues to stick. We want tape to stick. And by the same token, we want other surfaces to be non-sticky. Your frying pan, you want to be non-sticky. Your car windshield, you'd love to have that be non-sticky so that other materials didn't adhere to it. And this property is the direct result of bonding right at the material's surface. Sticky substances refer to a whole group of atoms and materials where atoms at the surface want to bond to other elements. They're right there sitting there. The electrons aren't quite properly distributed. They're just waiting for another material to come along and satisfy their bonding needs. So tapes and glues have this property of a not quite satisfied bonding, and therefore they're sticky. There are lots of good adhesives out there because there are lots of materials that aren't quite bonded in the way they'd like to be. But a real challenge in chemistry is to find non-stick substances. Imagine a paint surface, for example, that was so non-stick that you couldn't spray on graffiti, that you sprayed on a paint and would just wipe right off without the slightest bit of difficulty. Well, it turns out that such materials are in development right now. Indeed, there's a whole new class of materials based on fluorine that has this property. And the strategy here is to make a surface that looks to the rest of the world, for all the world, like an inert gas. Remember, inert gases are those atoms that just float around in the air. They never bond to anything because they have a completely filled shell. If you can create a surface on a material that has the same kind of look, every electron in its place, I don't want any more, I don't want to get rid of any electrons, it's not going to bond, and that will be a non-stick surface. So this is a hot topic in chemistry today. Our fourth property, magnetism. This is another vital property of materials. Permanent magnets are those materials that possess the ability to attract iron and other magnetic materials. You've all seen this with refrigerator magnets. You can take a magnet and pick up all sorts of things, almost like magic. Well, what is the property of a magnet, of a permanent magnet, that allows it to do this? I want you to think back about the lectures on electricity and magnetism and recall that an electromagnet, nothing more than a coil of wire through which you pass current, creates a magnetic field because electrons are moving around in a loop over and over again. And the electrons circulating in that loop create what we call the dipole field with a north and a south magnetic field. Now, imagine an atom. An atom with electrons in orbit around the nucleus are in effect tiny little magnets. At least they can be. In many atoms, the different paths of the electrons cancel each other out, so the atoms themselves aren't magnetic. But in a few elements like iron and nickel and cobalt, the electrons amplify each other. They align in the same sorts of orbits, and you have little atomic magnets. Each atom becomes a dipole magnet. Well, if you then take some iron, melt it, and crystallize that iron in a magnetic field that's imposed from the outside, all those atoms may align themselves. So you have one continuous array of atoms, all with their little dipole fields aligned. That gives you a permanent magnet in which there's a large external magnetic field. And that's the kind of thing you use in a refrigerator magnet. Now, the effectiveness of a magnet can be destroyed simply by heating it, because that ruins this alignment of atoms. It also often can be destroyed just by beating it with a hammer, because in that case, you're randomizing these orientations, and each atom then loses that alignment, which led to the collective property of the magnetic behavior. I want you to think about what happens to a magnet when it is subjected to a magnetic field. Okay, you have a magnet, and you apply a magnetic field to it. Think about this. Every one of those little atomic magnets then experiences the magnetic field, and as a result, the atoms have to shift slightly in position. Indeed, when you apply a magnetic field to a magnet, or when you change the shape of a magnet, you actually change the magnetic field. You change the shape of the whole material as it's being subjected to that magnetic field. So this becomes a very important technology. You can actually use magnets to create a microphone, and this is how it works. As you talk into a speaker, you have a diaphragm. The diaphragm moves. As it moves, it can change the magnetic field near a magnet. The magnetic field then is modified by the magnet itself, and signals are pulsed through the wire. And this is the principle behind many microphones and many speakers, using magnetic fields that vary simply because of the behavior of the atoms as individual magnets. The fifth and last material property I want to discuss is electrical conductivity. This is the ability of a material to carry an electric current. One of the most important properties of materials in modern life is their ability to control the flow of electrons, of electricity. Now, electrical conductors and insulators are both essential parts of this process. Good electrical conductors include all the materials in which electrical charges flow easily. That's electrons flowing through the material. And the most common of these materials are metals. Metals, by definition, have electrons that are free to move under the slightest voltage, the slightest push, and they'll move. All known materials have some resistance to this electrical flow at room temperature. And that causes heating of wires, and it causes a slight loss of electrical energy. But nevertheless, copper, aluminum can be used as wires, and electricity will flow through these for many, many miles. So that's why most common wires used in everyday use are formed of copper. Typical copper household wire is found in every home. Most household electrical wiring also can use aluminum in various places, though we know that gold and silver would make much better conductors in our homes. Those metals are just too expensive for normal use, although they find specialty use in many applications of electronic sorts of devices. There's another kind of conductor as well. These are called fast ion conductors, a strange kind of conductor in which instead of electrons moving, actual atoms, charged atoms, the ions move through the material. And many batteries use these kinds of conductors. For example, lithium is a fast ion conductor. A lot of polymer scientists these days are trying to make conducting polymers. That is, carbon-based molecules, organic molecules that carry electricity. It's a difficult challenge, but if we could do it, someday there might be very lightweight, very inexpensive materials. You don't have to rely on expensive metals like copper. You could actually just use carbon-based. You could use plants to make your wires. That would be quite extraordinary. Now, on the flip side, we have insulators, electrical insulators, which are essential because they restrict the flow of electricity. We need that for efficiency. We need it for safety. When you plug in a wire, you don't want to get shocked, so you need a good insulator wrapped around that wire. The best insulators, as I think I've mentioned, are made from materials in which electrons don't move, things like ionically bonded materials. But the trouble is, most ionically bonded materials are very brittle. They don't make very good wires. So we compromise and use covalently bonded materials like plastics to wrap around the wires. Typical wire then will have a plastic coating around a metal core. And that's the way most wires are built. And they're amazingly flexible. You can tie wires in knots and crush them and abuse them in all sorts of ways. And they keep on working and working and working. Well, there's another kind of material that has a different kind of electrical conductivity. These are superconductors. Superconductors are remarkable materials that conduct electricity without any resistance at all. But all of these materials require extremely cold temperatures to work. New materials are being discovered, however, that keep raising the temperature limit. And these new superconductors that work at higher and higher temperatures, albeit very cold, are finding many new applications. Superconductivity was discovered by the Dutch physicist Heike Kamerlingh-Onnes in 1911 when he measured zero resistivity in a sample of mercury at 4 Kelvin, that's at liquid helium temperature. Onnes was one of the world's great authorities on extreme refrigeration. That's temperatures near absolute zero. He found that an electrical current, once started in his mercury, would flow for years without stopping. Such a property, electricity with absolutely no resistance, suggested many practical applications, from powerful permanent electromagnets that operated forever to no-loss electrical power transmission over long distances. Now, most of the subsequent research is focused on finding other superconductors that worked at higher and higher temperatures, and most of the research focused on metals in the early years. Eventually, an alloy of the metal niobium was found that worked at about 22 Kelvin, and that's used in many practical applications today. For example, if you've ever had an MRI, a magnetic resonance imaging scan, it uses liquid helium-cooled niobium superconductors. And there are many other applications as well. Now, I've said that properties are the result of atomic scale activity, but superconductor behavior remains very mysterious. No one's really sure exactly how it works. Typically, we talk about electrons that pair and surf along, following each other through an electromagnetic wave through the material, traveling forever on that electromagnetic wave. But it's still rather difficult for any of us to imagine how superconductors work. I want to tell you one more story about superconductivity. In 1986, a whole new class of amazing high-temperature superconductors was discovered. It was first discovered in Switzerland at the IBM Zurich laboratories, and quickly other researchers began to work on this problem. I got sucked into this in February of 1987 when the University of Houston scientist Paul Chu, a physicist who had been spending his life on superconductivity, invented the first superconductor that worked at liquid nitrogen temperature. The extraordinary thing about a superconductor working at liquid nitrogen temperature is that liquid nitrogen is very cheap. You can carry it around in a jug, in a thermos bottle. You can actually use it in everyday applications. And this transformed superconductivity for something which is an esoteric and strange phenomenon to one that could be demonstrated on a tabletop. All one needs to do is pour liquid nitrogen on the high-temperature superconductor, and it begins to work. And we'll see how this happens in just a minute. What Paul Chu asked me to do, and my colleagues, was to determine the crystal structure of this new material, this new black, enigmatic material. You see, in order to understand how a material works, you have to know the atoms it's made of, and you have to know its crystal structure. Paul didn't know either of those two things. So our laboratory, a laboratory, by the way, that stressed geological materials, and so we were no threat for stealing the patents of a superconductor, believe me, we determined the composition and the crystal structure of this material. And those results were reported at an incredible meeting called the Woodstock of Physics, in which 4 other groups reported the exact same information that we had worked so hard to find on the same evening at the same meeting, with thousands of physicists looking on in an absolute bizarre, crowded and mob scene. It was a great time. Well, no one is still sure how these high-temperature superconductors work, but a lot of people are still working on it. I want to demonstrate one of the really fascinating properties of these high-temperature superconductors. I have here a black disk of this amazing material that Paul Chu discovered. If we pour liquid nitrogen on that material, it cools it right down, cools it down to about liquid nitrogen temperature. And as that disk is cooling, the superconducting is beginning to work. Now, one of the properties of superconductors is that they repel a magnetic field. They push magnetic fields right out. So a magnet material, levitates above the disk. And so as that disk is cooling down, we'll place a small magnet on top of it and see the levitation. We have to get rid of a little bit of the liquid nitrogen to make it work. I'll place this right on top of it. And there you see the magnet's actually floating. It's floating on top of the disk. This wonderful property of superconductors can lead to levitating trains and other transportation techniques where we just literally lift giant objects off the ground and float them to their destination. This is the property of high-temperature superconductivity, and now we can use cheap liquid nitrogen to achieve this goal. Well, in this lecture, we've seen the close connection between materials' physical properties and the atoms and the way they're bonded together. This is true for the strength of materials. It's true for their thermal expansion, for their stickiness, for their magnetic behavior, and of course for their electrical conductivity. And it's true for all the other properties of materials as well. Now, of all the high-tech materials of our new age, none plays a more significant role, none defines our society more than the semiconductors, which are the heart of modern electronics. And that's the subject of the next lecture.